In this video, we are going to talk about the electric field on the axis of a uniformly charged rod. What is a uniformly charged rod? See, we have a rod, okay, of length L over here, and there is a charge Q which is uniformly distributed on this rod. So if I take any section of this rod, then you will have constant charge per unit length. That means the lambda, that is the charge density, is constant per unit length. Charge per unit length is constant. So for the whole length L, there is a Q, so there's lambda is equal to Q by L, right? Okay. So now let's find out the electric field on the axis of this uniformly charged rod. Let's say I have a point P over here at which I want to find out the electric field due to this uniformly charged rod. Let's say that point P is at a distance A from this end of the rod, right? Okay. Now I can see all the charges are there. You can see the rod as a collection of all these positive charges. And then you can find out the electric field. You know the formula of the electric field. The electric field due to a charge Q is kq by x square, where x is the distance at which you want to find out the electric field. The problem here is that all the charges are not at the same distance from point B. So the contribution of the electric field by each charge will be different at point B, right? So now in that case, what you can do, you can assume this as a continuous distribution of charge, as a sea of charges, infinitely many positive charges. And now you can take a small element of a charge, okay, let's say dq element. This is a very small charge element, and the length of that element is dx, right? So very small length. Okay, now you can write the lambda as dq by dx, right? So dq is equal to lambda times dx. Okay, I will use this later. dq is equal to lambda dx. Now this dq charge is at a distance x from the point P, right? dq is at a distance x from point P. So here what I can see is the electric field due to this dq charge is small de, right? So this de is k dq by x square, right? It is k dq by x square. Now this dq is at a distance x, right? So it is k dq by x square. Now dq can be written as lambda times dx, lambda times dx by x square, right? Okay. Now you can see the electric field at point P will be varying as a function of x, right? The function of x, that is the distance from distance of the charges from this point P. Okay, now let's integrate that to find out the total electric field. So if I integrate it over dE, then I should get E, and that is equal to integral k lambda dx by x square, right? Now k and lambda are constant, so I can take it out, and this is 1 upon x square dx, right? Now I did this thing, okay, just simplification, but I have not written the limits over here, right? So where the limits will be from, right? So here if I start from here, this end there is a small charge here. If I start from that charge, then that charge is at a distance a from point B, right? So I have to go from point A, from A to this A plus L, right? A plus L. This is A plus L, from A to A plus L. So this will be equal to k lambda 1 upon x square dx integral is equal to minus 1 upon x, right? It will be minus 1 upon x, and the limits are a plus L and a, right? So this is k lambda minus a plus L minus 1 upon a plus L plus 1 upon a, right? So this is going to be the electric field. Now here this will be equal to k lambda 1 upon a minus 1 upon a plus L. So this will be lambda can be written as kq by L. This will be a plus L minus a upon a into a plus L, right? So here you can cancel out this a, and you have kql upon L into a plus L, right? So this L and L gets cancelled out, and you have kq upon A into A plus L. Right? So now the electric field due to this dq charge at this point P is in this direction, right? And all these positive charges will have the electric field in the same direction. So that's why I didn't write the direction here in this first place, right? So now you got the final result as kq by A into A plus L. Now how will I know that if it is correct at all, right? So see, let's see why it is correct or not. If it is correct or not, how we will see? If this is A into A plus L in the denominator, this is the electric field due to the rod. So now if I compress this rod in such a way that I make it a point charge, right? So that L will become 0. So if the rod has a length 0, then that system is same as having the whole charge Q at this point A from the point P. Now in this case, if I put L equal to 0 in here, okay, for L equal to 0, I am getting the electric field to be kq by A square, which is correct, because if a point charge Q is here at distance A from the point P, then it should have kq by A square as the electric field, right? So that means whatever we have derived is correct, right? So this was the electric field on the axis of the uniformly charged rod. Okay, in the next session, we will look at the electric field on the equatorial position, or you can say little off from the equatorial position of the rod. Okay, let's look at that in the next video.